All right, so now we're going to talk about quadric surfaces. The book has some awesome pictures, and so I'm just really not going to be the one to destroy that. So I'm going to refer you to the book for the pictures, but let's look at them a little briefly here, and I do mean briefly. So quadric surfaces are the graphs of equations that can be put into this general form. So after reviewing the textbook, you should be reasonably familiar with the following quadric equations. Now I'm going to write them as if they're, well, maybe the word centered is not perfect, but centered at the origin. And of course, if you have the D, E, F, G, H, J terms, then things are a little different and you have to work a little harder in terms of factoring, completing squares, etc. So again, some things that we've done before, specifically in Math 76 or in Calc 2. Okay, so what is an ellipsoid? Well, we actually, I think, talked a little bit about, well, we talked about a circle, a sphere. But an ellipsoid is kind of what it sounds like. It's like an ellipse, but not. So the equation for an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. It looks just like an ellipse. A hyperboloid of one sheet is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Notice that that somewhat resembles the equation of a hyperbola. A hyperboloid of two sheets, for that one, it just means that everything's negative, well, so to speak. So instead of a plus y squared over b squared, we have a minus. An elliptic cone is x squared over a squared plus y squared over b squared minus z squared over c squared, and I'll bet you're thinking she's made a mistake, but it equals 0. So an elliptic cone is kind of a misnomer. What it looks like is that it's two coins. It looks like it's two cones joined at their tip, the point. An elliptic paraboloid is given by z over c is equal to x squared over a squared plus y squared over b squared, which just looks like a parabola that's been sort of rotated around. And a hyperbolic paraboloid, z over c, is equal to x squared over a squared minus y squared over b squared. So if I wanted to sketch that and you wanted to cry, I could, but it looks like we have sort of two little earmuffs that are pointing opposite directions, so to speak. Right, so it looks like two little cups pointing one left and one, I'm sorry, that's z equals, one up and one down. Okay, and that's the idea. And of course, if we could have x over a equals y squared over b squared plus z squared over c squared, in which case we'd have an elliptic paraboloid that's on the x-axis. It's sort of recognition, just like when you were talking about conic sections. In fact, if you take cross sections of any of these, you obtain conic sections. And so I have some suggested exercises. One of the things that I'm having you think about in these exercises is also how, if the equation doesn't look perfect, can we fix it? So if I had something like x squared plus y squared minus z squared plus 2x equals 18, for example, right? I would do x squared plus 2x, complete the square, so I'd have a plus 1, a minus 1, plus y squared minus z squared equals 18. So that would give me an x plus 1 quantity squared plus y squared minus z squared equals 19. and then just divide through by 19. X plus 1 squared over 19 plus y squared over 19 minus z squared over 19 equals 1, if you want to get it into that form, and that's the idea. Okay, so I promised a short one, and so that's actually it. Next time, we're going to talk about vector valued functions. Have a great day.